Okay, I agree. All right, ladies and gentlemen, we are going to be using all the tools that we've created so far to learn how to solve these big polynomial equations, okay? So before we begin, what is the degree of my polynomial equation that you see on the board? 4, 3. So I can have up to 4 zeros. Some of them might be real, some of them might be imaginary or complex, but I can have up to 4. So we're not looking for 17 zeros here, right? Okay, where is a good place that we should start? I mean, we have to get some kind of a list of things that could possibly be. Yeah, the rational zeros theorem. Okay, let's start there. So that means I'm going to have all the factors of the last constant term. So plus or minus 1, 2, 3, 4, 6, 8, 12, and 24, all divided by plus or minus 1. So that's basically every single number in the numerator, right? Because I'm dividing by 1. That's a lot of numbers to potentially start with. I would not want to have to do synthetic division for each of those one at a time, like some people did in their homework last night. That'd be terrible, right? Okay, so instead, let's be smart about it. Let's use a calculator, and let's use some technology to help ourselves out. All right, let's see here. We're going to plug this into our calculator, this function. So I'm going to clear everything out. We're going to go x to the 4th minus 6x squared minus 8x plus 24. Yeah, okay, good. All right, good. So let's hit graph. Okay. It looks like 2 is a double root, or multiplicity 2. So it looks like 2 happens twice, right? But for right now, let's just use the fact that 2 looks like it's a 0, okay? So I'm going to go ahead and check 2 and use synthetic division. Now, what am I looking for when I do synthetic division here? Yeah. So I'm going to have 1, 0, because I have no x cubed term in my polynomial. So 1, 0, negative 6, negative 8, 24. Yikes, can't write. 24, and then that's good, right? Okay, so we're going to add here. So this gives me 2, 4, negative 2, negative 4, negative 12, negative 24. Hey, sweet, 0. Awesome. So because I have a 0 there, the factor theorem says that 2 is a 0 and x minus 2 is a factor. But what does this represent? Yeah, my new polynomial, which is representative of x to the 3rd plus 2x squared minus 2x minus 12, and it's still all equal to 0. Well, that's not a quadratic, is it? Because it's a 3rd degree polynomial, so I have to do this process again with this polynomial now, because I've already factored out an x minus 2 from my original polynomial. Okay? Now, if we go back to the graph, we can see that this is where 2, being a double root, comes into play. So I have a couple of choices here. I can either generate a new list with my new polynomial. So my possible zeros are plus or minus 1, plus or minus 2, 3, 4, 6, or 12, because I have a new list of possible rational zeros. And you'll notice that 2 is also in this list. So I'm going to go ahead and use 2 again on my 1, 2, negative 2, and negative 12. Because this is a cubic, not a quadratic. Yeah, she said, why do you have to do this again? And the reason is because we haven't broken it down to where we can solve it in a quadratic form. All right? So we're going to do it. Yeah, so same process. We're just repeating it. So I'm going to get 2 there. I'm going to get 4. I'm going to get 8. I'm going to get 6. I'm going to get 12. I'm going to get 0. This is good news now, because what does this part represent to us? Yeah, x squared plus 4x plus 6, which is what type of polynomial, ladies and gentlemen? Quadratic, and we are very good at solving quadratics. A is 1, B is 4, and C is 6. So I'm going to have B squared minus 4AC. So I'm going to have 16 minus 4 times 1 times 6. That's 16 minus 24. That's negative 8, huh? Is that right? All right, negative 8, 16. Yep, that looks good to me. Great. So then when I plug in, I'm going to have x equals negative 4 plus or minus the square root of negative 8 all over 2. All right, I have to deal with this square root of negative 8. The square root of negative 8 is equal to the square root of 8 times the square root of negative 1, which is the square root of 8i. I can break that down even further, though, can't I? 2 root 2i, very good. 2 root 2i. Or 2i root 2, wherever you want to put the i, it doesn't matter to me. So then I got x equals negative 4 plus or minus, I go 2 root 2i, all divided by 2. And I can simplify this fraction and get negative 2 plus or minus root 2i. So when I'm all said and done, the solutions, or the zeros, or the roots, or the x-intercepts, all of these things mean the same thing. They are 2, negative 2 plus root 2i, and negative 2 minus root 2i. Okay, so in your families, please try and solve this polynomial equation. X to the fourth minus 6x to the third plus 22x squared minus 30x plus 13 equals 0. I will tell you right now, your zeros are a mix of real and complex. All right, you guys, wherever you're at, we have to move it on. Wherever you're at, so take a look here. Okay, first of all, you should have realized that 1 was a root. Okay, 1 was a root twice because of double root. And as you cruise down, you should have found your answers for your zeros are 1 and 2 plus or minus 3. Seth. Okay, so far, here's what we've been doing as an overview, all right? So I've been giving you a polynomial, all right? And from that polynomial, we've been doing a bunch of work, and we've been generating the zeros. Okay, that's what we've been doing so far. Does that make sense to you? So, as an overarching theme, what we've been doing, right? Okay. For now, this next part, I'm going to give you the zeros, and we're going to generate the polynomials. We're going to go the other way. Okay, that's the general goal of what's going to happen here. So, you're going to see something like this. So the examples or the I can't talk right now. The instructions, that's what I should more. Sorry, the instructions look something like this. Find a, and they will give you some degree. So we'll say a third degree polynomial. So find a third degree polynomial and whose zeros are 1 and 2i. Okay? So in the grand scheme of things, we've been given the zeros, and we want to generate the polynomial versus what we've been doing, which is, okay, here's a polynomial, go find the zeros. All right? So how do we set this up? Let's think about this. First, let's talk about what we have been given. We've been given some zeros, right? And what are the two zeros that we have been given? 1 and 2i. Now, you may or may not remember that in a complex number, if 2i is a 0, then its conjugate is also a 0 because the conjugate pair theorem says that they come in pairs. Okay, so if 2i is a 0, then I know that negative 2i is also a 0, and that's the kind of one that you get for free. All right, this is very, very similar to this idea right here. Notice I have 2 plus or minus 3i. Both of those were zeros because it's a complex number and they happen in pairs. Okay? So if I'm given the fact that 1 and 2i is a 0, I am guaranteed that the conjugate of 2i, which is negative 2i, is also a 0. Okay? So now I have a list of 3 zeros. Everybody cool with that part? Yeah? Okay, so I'm highlighting and putting a star next to that one that we get for free. If these are my zeros, can we then talk about my factors? Okay, if 1 is a 0, what does the factor theorem says the factor has to be? No, the factor. X minus 1, very good. Okay, if 2i is a 0, what does the factor have to be? X minus 2i, right? And if negative 2i is a 0, what's the factor have to be? X plus 2i. It's always x minus whatever the 0 is. Very good, Seth. So now we can talk about the polynomial. So first I have my zeros. my zeros, and then I turn my zeros into my factors. Okay? Then I take each of my factors and I multiply them together to generate the polynomial. X minus 1, x minus 2i, and x plus 2i. Okay? I suggest that we do this part first. Okay? Let's do that part first. So on the out, I'm going to have an x minus 1. This is going to give me an x squared plus 2xi minus 2xi minus 4i squared. All right? Is that right? Good. Let's clean this up a little bit. X minus 1. Well, that's not x minus 1. X minus 1. We're going to have x squared. Let's see here. This and this go away, right? What's a negative 4 times I squared? Positive 4. Very good. Now all you do is multiply these together. What? Isn't this beautiful? That's so cool, right? All right, so what's x times x squared? Okay, and what were we supposed to find, you guys? A third degree. Oh my god, there's the third degree. It's so rad. Okay. All right, so x to the third, then what? Plus 4x minus x squared minus 4. So we're all said and done, you guys. The function that we're looking for is this. X to the third minus x squared plus 4x minus 4. Yeah, go away. Woohoo! And that is a third degree polynomial function whose zeros are 1, 2i, 3, and 2 plus I. Okay? So a little bit more challenging because of the complex number is not just a 3i or a 5i, it's 2 plus 3i. Same process though. Here we go. Let's see if we can write this out. Let's talk about our zeros first of all. Which ones are we given? 3 so 3 and 2 plus I. So what's the other one we get for free? 2 minus I. That's the one that we get for free because we know that zeros, complex zeros occur in conjugate pairs. All right, so if that's my zeros, let's talk about my factors then.
Wait, so unless you have 3 imaginary zeros,
there will be no x-intercepts. Correct. So if 3 is a 0, what's my factor? X minus 3. Good. If 2 plus I, now think of this, you guys, as an entity, as a number in itself. So that means I'm going to have x minus 2 plus I. Yeah, we're going to get there. Okay, if 2 minus I is a 0, then think of it as an entity, so it's x minus 2 minus I. Okay, so I had a 0, I turned it into a factor, 0 turned it into a factor. From there, I'm going to multiply all my factors together to create my polynomial. Is this making sense to you so far? Okay, now here is where you need to be really careful with your signs. So x minus 3. Let's distribute here. This is going to be x minus 2 minus I, and then x minus 2 plus I. You with me on that? Okay, I highly suggest that we do this part first before we multiply it by x minus 3. For this, I like to introduce the box method. X minus 2 plus I. I want to multiply it by x minus 2 minus I. Has anyone ever seen this before? Okay. Yeah, it's all I'm doing is distributing, except I'm doing it in a more neat way. Okay? So x times x is x squared. Negative 2x, xi. Negative 2x, positive 4. Does anyone know what I'm doing right now? Okay. Negative 2i. Negative xi. Positive 2i. Is that negative I squared? Okay, good. Let's clean this up a little bit here now. Some of them go away. Yeah, exactly right. So I still have an x minus 3, right? Don't forget about this point right here. I still have x minus 3. Let's clean this up. I have an x squared, yeah? The cool thing about it is you can kind of, as you go by, you can circle them. So, and then I'm going to have a negative 4x, yeah? These two, right? Okay, and then notice that this one and this one cancel each other out. Right? Ooh, so do these. Sweet. Oh, and then 4. And then, wait a minute, negative I squared. How much is negative I squared? 1. So 4 and 1, how much is that? Ooh, that was easy. Okay, so now I still have to multiply these two together. So for that, I'm going to introduce another box. I think it's a little bit more neatly organized, and I'm all about that. Okay, so let's see here. It's going to be x to the third. Hey, there's that third degree polynomial. Okay, I kind of, okay. 5x, what's the next one going to be? Negative 3x squared, very good, then what? 12x, then what? Now the cool thing about the box method is if you write your polynomials in standard form, then the diagonals are always guaranteed to be like terms. Oh, sweet. So we're all said and done, ladies and gentlemen, f of x. All right, come on, let's finish that. We're doing really well. Okay, so we're all said and done. We get x to the third minus 7x squared plus 17x minus 15, and we have now found the third degree polynomial with the given zeros right back up there. Pretty sweet, right? Okay, so if I were to graph this function, where would it cross the x-intercept, you guys? 3. Very good, because, well, you wouldn't see these because these are complex numbers, right? They wouldn't be on the real number line. So you'd only see one solution for that one, right? But that doesn't... Okay. Ladies and gentlemen, for the last idea of the day here, okay, we're going to do the same exact thing, except we're going to add in one more condition to our polynomial, and the condition is that, in addition to having zeros at negative 2, 2, and I, f of 3 has to be negative 150, all right? So we're adding in an extra condition here. So it's very important that we understand this process. So we're going to start the same way, all right? Let's see here. Yeah, we're going to find a fourth degree polynomial in this case. We're going to find a fourth degree polynomial. So my zeros are negative 2, 2, I, and, very good, team. That's the one that we get for free because it's a conjugate. We love it. Life is good. So let's talk about our factors now. Our factors are, if negative 2 is a 0, what's the factor? X plus 2, very good. If 2 is the 0, what's the factor? Very good. If I is the 0, what's the factor? X minus I, very good. And if negative I is the 0, you guys know what I'm saying. Okay, X, good. Good. So look, I have 4 things here. I'm going to then multiply them together to generate my polynomial. So I'm going to have x plus 2 times x minus 2 times x minus I times x plus I. Okay, I'll speed up the process a little bit and tell you that when you multiply all of these together here, you end up with x to the 4th minus 3x squared minus 4 when you multiply those together. That's good. So in other words, if we were in our last problem, if this was our last, the directions were the same as the last 2 problems we did, we'd be done. Okay? However, we now have to fit in the fact that we need f of 3 to be a negative 150. So that means that f of 3 has to give me 150 out of this thing, right? Negative 150. That's my condition that I have to meet here now, right? So what does that mean? That means that when I plug in a 3, I need to get out negative 150, right? So negative 150 equals, but if you'll notice, if you plug a 3 into that, you don't get 150 out. You get something else out, don't you? So what we have to do is we have to generate, okay, I'm going to call it Q times x to the 4th minus 3x squared minus 4. Because I need to multiply it by a factor in order to get it. So let's plug in and figure out what Q has to be. Negative 150, some number. Yeah, I'm plugging in a 3 to this one, right? So I need a 3 to the 4th minus 3 times 3 squared. Yes, very good. So I'm at negative 150 is equal to Q times 50. So for our polynomial, the one that we came up with up here, it turns out that f of 3 is only 50. But we need f of 3 to be negative 150. So we're going to solve for this little Q thing here. Yeah, exactly. So the q value I'm looking for is negative 3. So what do I do with that? I take that and I multiply it by my function. So the function that I really want is negative 3 times x to the 4th minus 3x squared minus 4. Or, for a final answer, I'm getting negative 3x to the 4th plus 9x squared plus 12 when I distribute.
We did it. Story time.
So this function right here is a 4th degree polynomial whose zeros are negative 2, 2, I, and negative I, and in addition fit the description of f of 3 is equal to negative 1/5.